Hi, welcome to Harvard Applied Math 205, a graduate course in scientific computing and numerical methods. I'm Chris Rycroft, and in this video we're going to look at linear least squares problems. We're going to introduce this general framework that we can use for fitting polynomials and other functions to noisy data in a way that will minimize the difference between our function and the dataset. So there are some situations where you might not want to fit every last data point exactly. If our data has experimental noise or some other type of random perturbation, then fitting a curve that goes through every single data point precisely may really be overfitting and reading too much into the information that we have. And we saw an example of this in the motivation section for this unit. We looked at 11 data points and we showed that fitting a cubic through these data points was a good compromise. The cubic captured the overall trends of the data well, without trying to fit every last perturbation in the dataset. And in this video we're going to look at the methods we can use for performing this type of fitting. Let's now look at the problem formulation. We've got m data points that give us m constraints, and we're going to fit a function with n parameters. And specifically, we're going to fit a function that is a linear combination of n components. And here, m will be greater than n. So in our previous example, we had m equal 11 data points, and we were fitting a cubic with n equal 4 unknown parameters. So in terms of linear algebra, this is an overdetermined system. So if we write this out as a matrix, AB equal y, then our vector B of unknowns will be short and we'll have n components. Our vector y will have our data points and we'll have m components and be long. And our matrix A here will be rectangular of size m by n. And this will lead to a rectangular matrix system where we have this kind of tall, thin matrix. And because now there are more constraints than unknown parameters, in general, this is not a system that we can solve exactly. Since we can't solve this exactly in general, we're going to take an alternative approach of minimizing the residual that will define as r as a function of b is equal to y minus ab. And a very effective approach for doing this is the method of least squares. And specifically, we're going to find the parameters b that minimize the Euclidean norm of r of b. And as we'll see, minimizing the Euclidean norm is a particularly good choice because our objective here is differentiable. And that means that we can use many techniques from calculus in order to solve this problem. So our goal here is to minimize the Euclidean norm of r, and we can write this out as the square root of the sum of components of r squared. And we'll first note that minimizing the Euclidean norm is actually equivalent to minimizing the Euclidean norm squared. And if we work with the Euclidean norm squared, that allows us to remove this square root, and it gives us a function that is easier to work with and differentiate. And we'll therefore introduce phi of b, which is just equal to this Euclidean norm squared. And if we now look at the calculation of phi of b, we can write that out as just r transpose r, and we can expand that as y minus ab all transpose times y minus ab. And we can then multiply out the components, and that gives us y transpose y minus y transpose ab minus b transpose a transpose y plus b transpose a transpose ab. And we can combine the second and third terms, and that then gives us y transpose y minus 2 b transpose a transpose y plus b transpose a transpose ab. And the reason we can combine the second and third terms is that all of the terms in this equation are actually scalars. And we'll note that the transpose of a scalar is actually the same thing. And we can actually see here that the second and third terms in this equation are actually transposes of one another, and we can therefore combine them into two copies of the same term. So we'll know here that phi is a quadratic function, and by construction it's non-negative, and therefore it definitely has a minimum. The minimum might not be unique, but we definitely know there's at least one. So to find the minimum of phi, we'll differentiate it with respect to b, and then we'll search for a point where the derivative vanishes. And we've got two terms to look at here, and we'll consider them in sequence. And first we'll look at the term b transpose a transpose y. And we'll differentiate this with respect to b. And we'll simplify this, and we can see that this is just the same as differentiating b transpose c, where c in this case will be a transpose y. And b transpose c, if we write it out in component form, that's just equal to the sum from I equal 1 to n of bi multiplied by ci. And if we now apply a partial derivative to this, d by dbj, then the only term that we'll get from this is the corresponding term bj multiplied by cj. And therefore, this partial derivative will just give us cj. And so, therefore, the gradient of b transpose c would just be equal to c. And hence, for the term that we're interested in, the gradient of b transpose a transpose y, that will just be equal to a transpose y. So let's now look at the second term. And we're interested in calculating the gradient of b transpose a transpose ab. And we'll note here that a transpose a is a symmetric matrix that we can write as capital M. And we'll write the components of capital M as little m with subscripts. And to proceed, we'll rewrite our form b transpose mb in a slightly different way. We'll write this as b transpose times the sum from j equal 1 to n of the jth column of m multiplied by the corresponding component bj. And to represent the jth column of m, we'll use the notation of m colon comma j. And here the colon is used to signify that the row index can run over the entire range. And this notation is used quite widely and is also similar to how columns are represented in MATLAB and Python when looking at matrices. Let's now look at differentiating this expression with respect to a component bk. So we'll look at taking partial d by dbk of b transpose mb. And so here there are two dependencies of b in this expression, and so we'll apply the product rule. And so first let's look at differentiating the b transpose. So if we differentiate this with respect to bk, then we'll just pick out the bk term in this expression, and we'll therefore get the kth unit vector that we can write as ek transpose. If we look now at the second term, then when we do our d by dbk, then the only term in the sum that will contribute is the corresponding bk term. And therefore, the second term will become b transpose times the kth column of m. So now let's proceed and let's look at the action of our unit vector ek multiplied into the sum. And so what will happen is that unit vector, when multiplied against a column of m, will just pick out the contributions in the kth row. And so we can rewrite this then as the sum from j equal 1 to n of m of k comma j multiplied by bj. And the second term is then just b transpose times the kth column of m. So now that first sum is actually just equal to the kth row of m transpose multiplied by b. And the second term is just then b transpose multiplied by the kth column of m. And because m is symmetric, we can actually combine these two terms into the same thing. And so we're left with then 2 times the kth row of m multiplied by b. And so we therefore find that the gradient of b transpose mb is just equal to 2mb. And so therefore, the term that we're interested in, gradient of b transpose ab, is then just equal to 2 times a transpose ab. So if we now combine the two different derivative terms that we calculated, then we find that the gradient of phi is equal to minus 2a transpose y plus 2a transpose ab. And we now want to find the minimum, so we set grad phi equal to 0. And from that we can conclude that a transpose ab is equal to a transpose y. And it's rather interesting to compare this to what we started with. We started with an over-constrained system that was just equal to ab equal y. And after going through this argument, we find that for this least squares problem, we get back the same equation, but now pre-multiplied by a transpose on either side. And due to this pre-multiplication, we actually end up now with a system that is potentially solvable, because a transpose A is a square matrix, and therefore potentially now invertible. And these equations are referred to as the normal equations. So it would be first good to establish that there's a solution to these equations. And it turns out that the situation is rather promising. And suppose now we consider any rectangular matrix A of size m by n, where m is greater than n. So we can show that the matrix A transpose A is singular if and only if A is rank deficient, which would correspond to a degeneracy in the columns of our matrix A. So let's look at both sides of this proof. So let's first suppose that A transpose A is singular. So that tells us that there's a non-zero vector z such that A transpose AZ equals 0. And we could pre-multiply this by z transpose to get that z transpose AZ is equal to 0. And that therefore tells us that the Euclidean norm of AZ is equal to 0. And we could therefore conclude that AZ equals 0. And that tells us then that A is rank deficient. So now let's look at it the other way. So let's suppose that we have a rank deficient matrix A. So we know then that there's some non-zero z such that AZ equals 0. And hence we can pre-multiply that by A transpose. So we know that A transpose AZ equals 0. And therefore we know that A transpose A is singular. So we've therefore established that there's a one-to-one correspondence between these two properties. So therefore, if A has full rank, so specifically then that the rank of A is equal to n, then we know that we can solve the normal equations and actually find a unique minimizer for the parameters b. So this is all good news. However, unfortunately, it's in general a bad idea to solve the normal equations directly. And the reason for this is that it's actually not as numerically stable as other approaches that we could take. And specifically, we find that the matrix A transpose A is typically poorly conditioned. So we can now ask ourselves a question. If we can't use the normal equations and solve them directly, then how can we actually solve least squares problems in practice? So it turns out that we can solve linear least squares problems while avoiding the poor conditioning issues associated with solving the normal equations directly. And to demonstrate this, we're going to consider a specific example where we consider the function y equal cosine 4x. We'll take 50 samples of this function at equally spaced points xi over the range from 0 to 1. And we're now going to try and fit a polynomial of degree 11 to these data points. And so we'll write our polynomial as the sum from k equals 0 up to 11 of bk times x to the k. And one thing you'll notice here is that we're expressing our polynomial in terms of the monomial basis. And you might ask why we're doing this after we showed that using monomials, was often a poor choice in other situations and led to poor conditioning problems. And we saw that, for example, the Lagrange polynomials could give us better conditioning. However, here, when we're dealing with fewer parameters in our function than data points, it turns out that the nice properties of Lagrange actually no longer apply. And therefore, it's often just as effective to use monomials. And here then, we're now going to try and find our polynomial that satisfies p of xi with the parameters b is equal to cosine of 4xi. And we're going to try and do a linear least squares fit of this problem. And this will lead us to an overdetermined system. If we wrote this out as AB equal y, then our matrix A here would look like a truncated van der Monde matrix. So it would be a 50 by 12 matrix, and it would be like taking a full van der Monde matrix but just truncating out 12 columns. We'll now take a look at the program lfit.py that can do linear least squares fitting. And here we're going to fit an 11th degree polynomial to a set of data points. So the first thing that we'll do is define a function here that can evaluate our polynomial that we're going to fit. As this will have 12 parameters, and this function vand underscore f will calculate our polynomial at position x for a given set of parameters b, and it will do this evaluation using Horner's method. That's an efficient way to evaluate polynomials that we described in previous videos. So we'll now go ahead and create our data, and for our x values we'll make use of 50 linearly spaced points over the range from 0 to 1, and for our y values we'll set them to be cosine of 4 times the x values. We'll then create our matrix A for this problem, and we'll make use of the numpy.vander command, and we'll pass in our x values, and we'll also pass in now this additional value of n, which is set to our number of parameters 12, and this will, rather than return a full square van der Monde matrix, will just return the first 12 columns. So as mentioned in the slides, it's not necessary to solve the normal equations directly to solve least squares problems. And here we're going to demonstrate Python's routine called lstsq that can do this alternative calculation that avoids solving the normal equations directly. And we'll get into exactly how this works in Unit 2 of the course. And this function takes in a matrix A here, our rectangular matrix, and also our data values y. There's currently an optional argument that is required to avoid a warning in the most recent version of NumPy, and this sets the behavior for how this function detects singular values of the matrix. So the lstsq function actually returns several different results, and the 0th one sets the parameters that we are looking for here. So here we'll just use this 0th return value and ignore the rest. So this code will also solve for the parameters by just solving the normal equations directly. And so here we first calculate the transpose of A, and then assemble the matrix A transpose A. And so we'll now have to solve the linear system for the normal equations. And so that will therefore be governed by the condition number of this matrix A transpose A. So we'll take a look at what this value is. And then we'll just do our linear solve here of the normal equations. So we'll also look at the difference between the parameters that were found using the two methods. And we'll then plot the results by introducing a fine grid over the interval from 0 to 1 and evaluating our two fitted polynomials. So let me now go ahead and run this program. And so we see here that both routines, the lstsq function and the normal equation direct solve, fit the data points extremely accurately. and the two curves are so accurate that they just lie right on top of one another, and we can't really see any difference. But we can actually see, if we look at the output of the program, that the condition number of A transpose A for this particular problem is very large, actually on a scale of 1 over machine precision. And we would therefore expect that even though we can get small residuals, our actual fitted parameters might vary considerably. And we actually see that the difference between the two approaches has some considerable deviations on the scale sometimes of 0.1. And so while both the polynomials fit the data points very well, we actually find that these two routines have returned different values. And we can actually see this in more detail if we now rerun this program, but we make use of a larger interval for plotting the polynomials. So here we'll look over the interval from -1.5 to 2.5, and we'll rerun this program. And so we indeed see that far away from the data, because the two fitted curves actually have some significant deviations in the parameters b, then we see some large deviations in our polynomial away from the data. So we saw in the lfit.py example that if we solve the normal equations directly, then we could still end up with a small residual, and therefore a good fit to the data. And if we actually look at the residual for both the direct solve with the normal equations and Python's least squares fitting routine, then we find that both of them have fairly small residuals. And in this case, both of them actually fit our data points very accurately. However, if we go to larger problems, then we'll start to see more difficulties with using the normal equations directly. So far, we've dealt with approximations that are based on polynomials, but it's worth noting that the linear least squares framework can actually work with non-polynomial approximations as well. And the only thing that we require is that our model should depend linearly on the parameters. And to demonstrate this, we're going to look at another example of np_lfit.py. And in this case, we're going to approximate e to the minus x cosine 4x using a combination of exponentials. We're going to define fn of x to be the sum from k equal minus n to n of bk times e to the kx. And while we have nonlinear functions here, e to the kx, we'll note here that this expression f here is linear in the parameters b. We'll now take a look at the program np_lfit.py that demonstrates using the linear least squares methods to do non-polynomial fitting. And we'll follow the example that was introduced in the slides, where we now fit a combination of exponentials of the form e to the kx, where k can run from minus n to n, to a given function. And so to begin with, we'll define this maximum exponential size n, and that will then lead us to 2n plus 1 degrees of freedom to fit. And we'll then go ahead and describe a function sumxf that can evaluate our function to fit at a point x for a set of parameters b. And we'll now go ahead and describe the linear least squares problem. So we'll make use of 20 data points over the interval from -1 to 1, and we'll then assemble our A array. And here we'll make use of some of Python's shorthand commands to assemble all of the entries here. And so all of the entries here will be made of these exponentials evaluated at our data points. And for this case, our y values will be given by the function cosine of 4x times e to the minus x. So now that we've specified x, a, and y, we'll go ahead and call the lstsq function to find the set of parameters b. And we'll look at how well our fitted function matches the data by looking at the scaled value of the norm of the residual. So we'll now go ahead and plot the results by introducing a fine grid from -1 to 1 and then plotting our fitted function. So we'll go ahead and run this code. And so here, when we're making use of n equal 1 and 3 degrees of freedom, we see that the curve that we fit, while it captures some trends in the data, does not do a pretty good job at really capturing everything that we see. And we also see here that the value of r here is considerably large. So now we'll go ahead and increase n to 3. And we'll run this program again. So now we're going to make use of 7 degrees of freedom. And we now see that the fit is considerably improved, although there are some small deviations that we see towards the ends of the interval. And our scaled residual here is on the scale of 10 to the minus 3. So we'll increase n once again to 5. So we're now fitting 11 degrees of freedom. And we'll run the program one more time. And now our fitted curve is near indistinguishable from our data points. And that's also reflected in our scaled norm value of 7 times 10 to the minus 6. So let's now revisit the normal equations. We have A transpose AB is equal to A transpose Y. And if we were to solve this system and find B, then we could apply the matrix inverse of A transpose A. And we would find then that B is equal to A transpose A inverse times A transpose Y. And this motivates a new definition called the pseudo-inverse that we denote as A superscript plus. And this will be true for rectangular matrices with m rows and n columns. And here we're looking specifically at a case when m will be greater than n. And so we'll define then our pseudo-inverse to be A transpose A inverse times A transpose. And that's specifically what we would need to find B in terms of y. So B would be given by the pseudo-inverse multiplied by y. And the key idea here is that the pseudo-inverse actually generalizes the idea of a regular inverse. And suppose that we actually plugged a square invertible A into this definition, then we could see here that the pseudo-inverse, we would get A transpose A inverse times A transpose, and we would then be able to get two factors of A that would cancel away, and we'd just be left with A inverse. So we can also note that even if A is not invertible, we still have that the pseudo-inverse multiplied by A is equal to the identity. However, the other way around, if we do A multiplied by a pseudo-inverse, then in that case, we won't get the identity in general. And hence, because of these two properties, we often refer to the pseudo-inverse as a left inverse. And so we have then that we could solve these normal equations using B equals pseudo-inverse of A y. And so that would then give us like our least squares solution for a rectangular matrix. And it's worth noting that we would define the pseudo-inverse slightly differently in different cases. And here we're specifically focusing on the case where m is greater than or equal to n.